click that record button. You want to repeat that slide real quick?
Yes, I will repeat the slide. So let me just, okay. So first we're talking about arrays, and arrays are the simplest way to keep a sequence of values in an ordered manner. And arrays are a Java generic type that allows you to pick a type and have a sequence of those type values stored inside the structure. And one thing to note about arrays is that their size is fixed. So you decide on the size when you declare it, and you cannot change it afterwards. And the way you access array values is by using square bracket notation. So use a square bracket and put in the index number, and that is how you access and modify array values. And there are three main ways to initialize an array, just for review. The first one is by using a the new keyword to create an array of a specific length without putting any values inside of them. So this array is initialized with no values specifically. Or alternatively, you can again use the new keyword and using the curly braces notation, directly input values you want into the array. And this array declared will have the size of the values that you already put inside of it. And the third way is pretty similar to the second way, but just the fact that you can actually omit the keyword new and the type if you're directly putting the values inside our curly braces notation. And very quickly, we're going to take a look at a fairly straightforward example of our arrays. And so I think we'll give people around 5-ish minutes to work on this, and then we'll come back together and walk through this question.
What are the values of access?
Feel free to put any questions you have in the chat or turn on your mic.
What the fuck?
Okay, how are we feeling about the question? I think we're ready to take it up.
Not ready yet.
Sorry, what was that?
Can I get some more time?
Okay, yeah, for sure. I'll give 1 or 2 more minutes. Yeah, so if you're done, you can use the reaction tab to show a thumbs up. That would be nice. So I can keep track of how many people is.
They made it now that thumbs up and stuff expire, which is really unfortunate for
Yeah.
this kind of thing. It's fine.
It's okay. I think we'll take it up in a minute. Once again, regarding any logistic midterm issues, we would really recommend reading through the ed posts. And if you have any questions still, ask on those ed posts because we have no idea, any more idea than you do. So yes, that'd be the best. Okay, I think we're going to go through this example now. So let's see. Okay, so we have our public class foo, and there are some variables that will be declared if we create this class. But first, we're just going to go into our main method to see what's happening here. So first, we have our n variable, and all it is an int that's number 3. So we have our n equals to 3. And then we are going to create our xx variable, which is a pointer to this new instance of a food class. So we have this thing called foo. Oh, sorry, this is wrong. It's not actually an instance of foo. What we have here is an array of foo. So what we actually have here is an array of size n. And as we have here in our n equals 3, so what this is an array of size 3. So we have our array of size 3 in our XX. Make sure to mute your mics. And in the same line, we declare this other variable called YY. And again, this is also another foo array of size n. In this case, it's 3. And so far, these arrays don't have any values in them. Now we go into this for loop, and this for loop is iterating through I minus n, which is in this case, again, 3. So in our first iteration of our for loop, we create this variable called f. And f is this time, actually, just to make this give myself a little more space, is this new instance of our class foo. And foo here has 2 variables that we would declare in them. So x and y, and they're going to be ints. But so far it doesn't have any values inside them yet. So now we go to this line and we take a look at f.x, which would be this variable, and we set it to I. And because this is our first iteration of our for loop, I is going to be equal to 0. And same goes for f.y. We are going to assign this value to I, which is again 0. And now what we do is we take a look at here, XX index I, which is going to be the first pointer or the first box here in our array. And we're going to set this pointer to point to this instance of our class. And again, we go into YY at index I, which is again index 0, and we point it to F. So this completes our first iteration of our for loop. And then we run through our for loop again. So now we have our second iteration of our for loop. We create another F. And just for simplicity's sake, I'm going to use the same variable pointer here. So we create this another instance of a foo class. Again, it has two variables, X and Y. And this time, f.x is still equal to I, but in this case, since this is our second iteration of our for loop, I is going to be equal to 1. And same goes for f.y is equal to 1. And then again, xx at index I, this time at index 1, which is going to be the second box here. We're going to set our new pointer to our new f. And then same thing here, we're going to set our new pointer to our new f here. Then we enter our third iteration of our for loop. We have then again another instance of our foo class, again with variables x and y. And this is our new f. And here we take a look again, we have f.x is equal to I, in this case is equal to 2. Since this is our third iteration of a for loop, same again, f.y is equal to 2. And then again, we set our pointers. Xx of index 2 is pointing to the same thing as f, and yy at index 2 is pointing to the same thing as index or as pointer f. And now we completed our code up to here. We take a look at the second for loop. Again, iterating 3 times since our n is equal to 3. First, we take a look at xx at index I, which in this case is 0. So xx at index 0, if we look at our pointers, let me just use a different color. This is the pointer we're looking at. It points to this for this instance of our foo class. And we take xx at index 0, this foo class dot y, which is this value, and we multiply it by 2. And 0 multiplied by 2 is still 0, so it's still 0. And then we take a look at yy at index I, which in this case is 0. And we follow this pointer to this instance of our foo class. And we take yy at index 0 dot x, which is this value is 0, and we multiply it by 3, which in this case is still 0. And then we go into the second iteration of our for loop. So now I equals 1. Xx of 1 is this pointer, so it points to this instance of our foo class. And xx of 1 dot y is this value. And we multiply that by 2 is 2. And again, yy at 1 is this instance. And dot x is this value, which multiplied by 3 is 3. One more time at index 2 is the same thing. We take a look at x at index 2 is this instance, y value, 2 times 2 is 4. Yy at 2 is this pointer, points to this instance. X times 2 is, or x times 3 is 2 times 3 is 6. And that concludes our for loop. And now we have completed executing the code. So then now here, what we need, we can actually take a look at the questions now. And first we take a look at xx at index 0. So xx at index 0 is going to be this pointer. And what do we have in this pointer? We have our 2 variables inside of our class instance. So first thing is x is equal to 0, and there's y equal to 0. Notice that I'm just writing these here, but when you actually try to access these values, what you need to do is you need to use our dot notation. But just for simplicity's sake, I'm only writing down x and y. And x of 1 is this pointer, which gives you x value of 3 and y value of 2. And xx of index 2, this is this instance, x is equal to 6 and y is equal to 4. And here, if we take a look at y index 0 is this pointer. You realize that these two actually point to the same instances. So all of its values will actually be the same. So x is equal to 0, y is equal to 0. Same goes to here. X is equal to 3, y is equal to 2. And this instance, x is equal to 6 and y is equal to 4. Does that make sense to everyone? Any questions? I see the chat has. Okay, if we're good, we're going to move on. Oh, let me clear this. Right, so here's just the answers again. You'll see that it's the same as what we did earlier. And here is just a neater diagram that displays the same thing if you want to refer to these slides later on. And so that's it for our array section. And if there are no questions, we're going to move on to talking about lists. Okay, doesn't seem like any questions. So let's take a look at a list. So what is a list? A list is a public, if you take a look at this code here, it's a public interface of a list. So it's an interface that basically allows you to store a collection of items in an ordered manner, which essentially gives the same basic functionality as an array. But the difference here is that there are a lot of different implementations of lists, since all it does is it provides an interface which gives you these methods that a list needs to implement, but doesn't actually give you any concrete implementation of a class or an object. So unlike arrays, lists are true objects and they're not a primitive type, which we talked about earlier of arrays being. So here's a link if you're interested or curious. You can take a look at the full list API, which gives you all of the methods that a list could potentially hold. But here are just the general list of the important ones that we're going to go over and cover. So just briefly discussing the differences or comparison between an array and list. So an array, again, has a fixed size, which is determined at initialization and can't be changed afterwards. And it does use square bracket notation for accessing values at specific indices. And arrays are available for use without importing anything or implementing anything. You don't have to import any libraries or classes. And arrays are in general a more simple implementation, but they do contain a lot less functionality. On the other hand, lists are, first of all, dynamic in size, in the sense that you can add and take away items in the list without having to create a whole new instance of a list, as you would have to in an array if you were to change the size. And the specifics of how we would change the size depends on our implementation of the list. So the different list implementations would have different ways of adding and removing values. And lists must be imported from java.utils or some other library because, as we talked about earlier, it's a separate interface. It has a different set of code. It's not simply just a Java primitive. And a list has a set of given methods that may be used and access modify elements. So that's the interface methods that we were talking about earlier. And the implementation of a list is much more complicated which you probably experienced or will experience in project 1 already. And however, they do give a lot more useful functionality to the users because of those extra methods that we have. So what this proves is that data structures are in fact useful. There is a reason that this class exists, and that however, even though lists are less intuitive and more difficult to implement, they are in the end easier to use and do offer more flexibility. Yeah, so I'm going to pass this on to Amit now, and he's going to take over and talk about the specific implementations of lists.
All right, cool. Thank you, Angela. Let me just go. See if you guys can see my screen. All right. I think you all can see my screen. Let me just make sure. All right, cool. All right, so let's get started with we've talked about the list interface, right? Keep in mind that the lists interface is not an object. So you can't actually make objects that are lists, but you can make certain other objects which implement the list interface. And also, we've talked about this before, but an interface in general, it's dictating how an object should behave. So the lists interface almost dictates how certain objects, which we'll go more into detail, like linked lists, array lists, how they should behave. So moving forward, let's move on to linked lists. So as you probably noticed in project 1 or just during lecture, linked lists are a certain types of lists where there's a very recursive pattern. And so the recursive pattern comes from how the objects in the linked list, they're linked by certain pointers. So each object is linked to the next object, which is linked to the next object, which is linked to the next object. So that's where the word linked list comes from. It's like almost a link or a chain of objects that makes up that list. All right, cool. So the first example that you've seen of linked lists in this class is the int lists. And basically, just by this diagram, you can see that the int lists are basically comprised of two attributes or two instance variables. Essentially, the first one, since this is an int list, the first attribute represents an integer. In this case, it's 3. And then the second attribute is almost a pointer to the next object in line. And what I mean by pointer is that it's a variable that's storing, it's pointing to the next object in line. So it's storing that next object. So essentially, when you land at an int list, you have a way to reach that next object, and you're going to use that rest keyword to reach that next object. So essentially, as you can see over here, there is a recursive structure where each int list item points to the next int list items. But there is a little bit of a trickiness involved with this, right? Suppose I decide that I want to store some numbers, and I don't know how many numbers I'm going to store, so that's why I can't use an array. So let's say I decide to use an int list. When I'm deciding to use this int list, as I add on numbers, right, there's certain things that I have to keep track of. What I have to keep is first I have to create a new int list, and I have to set that int list value to a certain number. Suppose in this case it's 5. But then I have to myself, as a programmer, I have to, dictate how these pointers behave. That's up to me. So you're gonna have to do something like int list.rest, or in this case, suppose this object, the variable.rest is equal to this new int list. And so it does become a little bit tricky, a little bit messy for the programmer to handle all these cases when you're just traversing through this int list. When you want a certain item, you're gonna have to work with these pointers, and it gets tricky, especially when you just want this object to solve a bigger problem, right? That's the whole reason why we have objects in the first place. We want to solve bigger problems. And so you don't want to get in too much into the nitty-gritties of these objects. And that's where the singly linked list comes from. So the singly linked list, if you look at this diagram, and if you look at this diagram, they're very, very similar, right? Almost the only difference that you can see is there's something over here for the singly linked list, and that this int list is replaced by another object called a node. So basically, the singly linked list is a encompassing class holding only the first node and size. We'll talk about that in a second. And the new difference that we also saw was that we changed the int list class to a private class called node within the singly linked list class. And you guys may be very familiar with this, especially because you may have seen this in project 1. But the way this works is essentially all the singly linked list class tells its users is this first variable and this size instance variable. So the singly linked list class, it's keeping track of a chain of nodes. It's keeping track of a chain of these nodes, and each node is keeping track of the next node in line, right? But the first node, who's keeping track of the first node? The singly linked list class, and specifically the first instance variable. And you also have this variable size. The reason why this is so much more preferred than the int list class is because when we will go back to our example, when you want to store a bunch of variables to solve a bigger problem, right? And you don't want to store them in an array, you don't know how many variables you're going to store, you want to store them in this linked list type of fashion. Why would you use this over the int list? Because the singly linked list, it makes the programmer, it allows the programmer to essentially add and remove items without dealing with this pointer structure. So if you've seen in your singly linked list class in project 1, there's probably an add last method, there's probably a add first method, or remove last, remove first. In project 1 specifically, you're working with a different type of list, but in general, you get the scheme of things, right? You don't have to deal with this pointers. You don't have to create a new node manually. And then say this dot node dot rest is equal to this node, because when you do add first or add last or any of the methods that are available to you, the singly linked list class will take care of that. And all you have to do, this architecture that you're seeing over here is all happening without, like, with your eyes closed almost. You don't have to worry about this. And that's basically the beauty of abstraction. We've implemented the abstraction in the linked list format. We started with the int list, and then we moved on to the singly linked list, where now we don't care about what's happening in the inner scheme of things. We don't care about what's happening between these nodes, as long as singly linked list class handles how to retrieve the first item, how to get a specific index, as long as that handles it for us. All right, moving on, we have Sentinel Nodes that are also a vital part of the singly linked list class. So basically, Sentinel Nodes are secret nodes that we add to our implementation, and they're invisible to the outside user. And essentially, the main reason why we have these is so that we can perform the same checks on an empty list that we can perform on any other list. And this may sound like a little bit of fancy wording, but I'll explain what that is for just a moment. So basically, we have this Sentinel, which basically we replace that with the first. So instead of this variable, now we just have a variable called Sentinel. And it's pointing to this node. And if you concentrate on this node, right, we're storing integers, but this node has a value called null. And so the way this happens is, suppose you initialize a singly linked list. Like you're working on a program, you decide you want to store some numbers, and so you initialize a singly linked list. When you initialize a singly linked list, right, if you had this implementation, you would have 0 nodes over here. You would have this section would all be blank. And because this section would all be blank, if you want to make a call to remove, or if you want to make a call to add, you have to keep track that this section is blank. So especially when you're making a call to remove, then you're going to have an if statement which says, okay, remove this only if this is not null, right? Whereas over here, when you initialize in this format, when you initialize a singly linked list in this format, you always create this Sentinel node. And the Sentinel node is not for the user, but it's not for the outside user because it's invisible to the outside user, but it's only for the sake of writing clean code and the sake of the class. It's basically so that you can almost treat every node as the same node. And so, yeah, that's pretty much it. And also the Sentinel node, keep in mind, this will be very useful for what we're diving into next, which is the doubly linked list. So now the doubly linked list and is basically a major improvement over the singly linked list. It does take a bit more space, but the reason why we have a double linked list is, suppose you're in a singly linked list, suppose you want to access this element. Suppose you want to access node 5, right? When you want to access node 5, if you say get this element, which is 0, 1, 2, it's the second, it's second in line, or yeah, it's the second index element. When you make a call to get and you pass in the 2, you pass in the index 2, what's happening behind the schemes is that the SLL list class is basically going to Sentinel. Then it's iterating through all of these until it finally reaches the second index, and it finally reaches this node, and then it returns that specific value that you want. However, imagine if you have 1,000 nodes. If you have 1,000 nodes and you want to access that last element, right? Or the second last element. If you want to access that second last element, right? And if you have 1,000 nodes, you want to access a 999 node, you would have to iterate through 999 nodes before you even reach this node. And then you return this node, and then you do that. And now, especially in a bigger program, when you're accessing a lot of times, or when you're removing things a lot of times, this does become a very, very complex, and it takes a lot of time. Especially, you can imagine if more than 1,000, you have 2,000 nodes, right? 2,000 is like almost like the biggest class in Berkeley is about 2,000 students, right? So if you're gonna keep track of all the students, you would need somewhere about 2,000 nodes, and that's just like a simple example. And so if you want to get access to this node, you would have to iterate all the way from the back and access that 2,000th node. That's where the DLL list class comes in, where essentially each node, the node class is the biggest difference in this. And what the node class is, instead of just having a variable called next, this pointer that points to the next item, it has a variable called previous that points to the previous item. So the DL list class, you can always think, if you go back one slide, you can always think of it as double arrows. So you can go forward and you can go backwards, and that's really the beauty of it. And so you can, in order to access the second last element, you can actually go backwards from the Sentinel. The Sentinel goes all the way back to the last node, and you can see that in this picture over here. This may not be the best example because it's just one extra node than the Sentinel, but imagine if you had 5 nodes, the Sentinel is almost like it's pointing to the first node and it's pointing to the last node. And so if you want to go to the second last node, you can almost go in any pattern you want. You can go counterclockwise, you could go clockwise. And that's really a key advantage of the W-link list. You may still see some sort of issue with this. Suppose you have 1,000 nodes, you want to access the 500th node. Either way, if you go forward or if you go backwards, there's still a little bit of complexity involved, because the 500th node, you're still going to have to iterate through 500 items, irrespective of which you go, right? And so there's still a little bit of complexity in there. And so we'll figure out how to solve that complexity later as we move on. For now, let's move on to a practice problem. So I'm going to read out this problem, take a minute to read out this problem, and then I'll give you guys about 5 minutes to really solve this problem. So the problem says is that given that we have this int list class as seen in the lecture, but with an added skipify method, read this prompt below. So we have this int list class, and suppose we define 2 int lists as follows. So we have 2 int lists right now. The first int list A has values 1, 2, 3, 4, 5 all the way till 10. Second one has values 9, 8, 7 all the way till 1. And so these are 2 int lists with these values. After we call the skipify method on each of these int lists, we get these as our returning values. So we get 1, 3, 6, 10. And then for B, we get 9, 7, 4. So see if you can find a pattern over here. Really, this question is a bit tricky because not only is it asking you to solve the problem, but it's also asking you to identify what the method does in the first place. So take a minute to identify what the method does in the first place, and then I'll give you guys about 5 to 6 minutes to try and conquer this problem. I highly recommend you have a piece of paper and a pen or a pencil, and so you can draw this out if that really helps. I apologize, but when we go over the solution together as a group, we won't draw it out. So really recommend, if you guys need it, draw it out and then take 5 to 6 minutes, and then we can come together as a group. And yeah, feel free to like unmute yourself for any questions or text the chat. All right, cool. Hopefully you guys didn't see that. If you guys don't know what I'm talking about, that's good. Anyone need more time with this question?
Yes, please.
Okay, yeah, for sure. Take a bit, like 1 or 2 more minutes. Okay, cool. Hopefully that was enough time. If not, don't sweat it. We just have to move forward because of time constraints. But yeah. All right. So the first things first, right? What does Skipify even do? Right? Anyone wanna be a brave soul and answer this out loud or in the
I
chat?
think
Go ahead.
I think like what it does is that actually it first of all it skips like one node, and then it skips 2 nodes, and then it skips 3 nodes.
Exactly, right? You can see that over here. There's a certain pattern where it's like this, the function name, you can tell it's skipping something, skipify. And in this case, you can see that it starts out by skipping the one node, then starts out by skipping 2 nodes, 4 and 5, starts out by skipping 3 nodes, and then eventually you reach the end of the list where you don't want to skip anything. In this case, right, starts out by skipping first node, then you start off by skipping 6 and 5, and then you start out by skipping 3, 2, 1. Oh wait, there's nothing else left. All right, that's it. Ended over there. So that's why you get 1, 3, 6, 10, 9, 7, 4. Cool. All right, so let's talk more about this implementation. How do we go about implementing this? The first thing that you should see, right, just the general structure, we have this variable n, and we have this variable p. And so a lot of times when the variable is given to you, you know it's going to be used somewhere else in the spec. So keep that in mind. The second thing that pops out, or that should pop out to you, is basically we have these 2 loops type of structures. We have this while loop that says while p is not equal to null, but we have this other loop structure, a for loop over here. And there's a blank over here, it's indenting I by 1, but there's a blank over here. And this 2 loop structure should kind of like dictate how you should go about this problem, right? We know we want to iterate through this just by intuition. We know we want to iterate through this linked list, but how would we go about skipping elements? And we're skipping elements at a weird fashion. We're skipping them at one, then 2, then 3. So we're not consistent with our skipping. So let's just dive right in, and I'll go over the solution. Let me move on. All right, cool. So we first start off with this next variable. What do we want to set this next variable to? And so there's 2 choices that we can really choose. First choice is we can set it to p, and the second choice is that we can set it to p.rest, since p is an int list. In this case, we're already given p. So my intuition and your intuition as well, as you build it over time, it will tell you that you want to set it to p.rest. And for now, you may not know too much about next because we haven't got deeper into it. It's being mentioned over here, but for now, let's set it to p.rest. Cool. Now we have this inner for loop structure. And anyone have any ideas what this inner for loop structure will be used for?
I think
Really?
just to see if the first element is null or not.
Yes, that could. So there is something that is there to see if the first element is null or not. But why would you want a for loop, right? Think about why there's a for loop, right? If you wanted to check if the first element was null, you would just do, if P is equal to null, is equal to null, right? You would have an if statement, but you have this for loop condition. You are on track with checking that something is null, and we'll get to that. But anyone have any ideas what this for loop will be responsible for? I'll give you guys a hint. Concentrate on this variable n.
There's a couple answers in the chat if you want to take a look at that.
All
There's
right,
a variety
cool.
of answers.
Yeah. Okay. Cool. Skipping the numbers needed to skip tells how many nodes to skip. Exactly, right? So this for loop is essentially, the while loop is responsible for going through the nodes, but this for loop, it's entirely responsible for skipping the nodes. So anyone have any idea what will go in this blank over here? I is less than n. That's exactly right. Perfect. We move forward. Oh, okay, I is less than n. We got that. Over here, we have this return statement. Anyone want to tell me why we have this return statement and what this return statement does, even though this is void? The method is void. What does this return statement do? Break. Someone said break. You can't advance it further. Yeah, to prevent a null pointer exception. Okay, cool. I'm getting a lot of variety of answers, but let me narrow down those answers. Basically, a return statement and a void, you're not returning anything, but think of a return statement as a break, not for the loop, but for the whole method. It breaks the whole method. It says end of story, bam, move on. And so this return statement ends the method. When would we want to end the method? When do we want to end the method? Right? We're iterating through how many items we want to skip, reaching null. Exactly. And so in this case, what are we checking? What are we checking which is null? When next is equal to null. Yes. We're checking when next is equal to null. P, why aren't we checking when P is equal to null? Because this while loop condition already confirms that. This while loop condition tells us the only reason why we're in this while loop in the first place is because P is not equal to null. So what we have to do is check that P.rest, which null, is not equal to null, or next is not equal to null. Good. Moving on to the next line, right? So now we're skipping over items. So what do we want to set our next to? We're skipping over something. Next is equal to next.rest. Exactly, right? And this is essentially, you might have seen this while iterating over any array, any linked list. You want to basically set that pointer. You want to set the next to the pointer of to the next list in line that's not next. And so you just say next is equal to next.rest. All right. Good so far. So now we've handled our skipping for now, right? But we're still iterating over the elements because we want to skip over certain elements, right? Over here, these lines become a little tricky, but over here, right? Now concentrate on what we want to set our P.rest to. Concentrate on what we would want to set that to. Exactly. P.rest, we want to set that to null or to next. And the reason being is because we're already at P, right? We want to skip over certain items, and next is basically a variable that's telling us which item we want to point to, right? This for loop, all this for loop is doing is it's ensuring that next is the next in line item that we're not skipping over again. So essentially when we do P.rest is equal to null, we're connecting our variable P to next, and next was the item that, or the node that we skip some nodes, and next is a node that we're not skipping. Cool. P.rest is equal to null. Finally, we have these two lines. It doesn't matter which order you do these two lines in, but it's the idea of where the semicolons are placed should give you where you would want these two lines. All right, I'm getting a variety of answers. Okay, yeah, P is equal to next. All right, cool. P is equal to P.rest. That is essentially what we're doing over here. And that you can convince yourself, right? Just by any iteration, we still want to iterate the bigger picture, right? We've iterated over the items that we want to skip, but we want to iterate over the bigger list, right? Because then after we skip 3 items, then we want to move on to the next item in the list and skip 4 items. Then we want to move on to the next item in the list and skip 4 items. P.rest is equal to next, right? Yes. You could also do that P is equal to next or P is equal to P.rest. Same thing, because right now we're setting P.rest equal to next. And so when you do P is equal to next, it's the same thing as saying P is equal to P.rest. Lastly, what's one thing we have to add over here? Something related to exactly n+++. And so the reason why we're adding that over here is because first we want to skip over one item, but then after we do our iteration over the bigger picture, then we want to skip over 2 items, and that's where we append n by, or not append, sorry, that's where we add 1 to n, and so n plus plus. Cool. Hopefully that made sense. If you guys are still stuck on this, I highly recommend you guys to come back to this and draw it out. Drawing it out always helps. But last element is null. All right, cool. I will leave Anjali to answer the questions, and I will move forward because we are running out of time. Oh. All right, we have another problem. So take about 5 minutes to read this, or I can read this problem for you. Essentially, we have a same type of problem. So hopefully the first problem, you got some intuition in how to go about iterating through a linked list. But in this problem, it's a similar structure, right? We have an int list class. We have the first and the rest variables that we can use. And so given a sorted linked list of items, we want to remove the duplicates. It's simple as that. So for example, if we're given 1, 2, 2, 2, 3, all we want to do is mutate it to become 1, 2, 3. And keep in mind, the keyword here is destructive. And so essentially what that means is that we want that same object to be 1, 2, 3, and we don't want to create a new list and tell that to be the non-duplicate version of this. All right. Makes sense. Take about 5 minutes, go through this, use the intuition that we developed before, right? Look at the structure. There's a while loop here. Why is there a while loop here? There's a current and a previous. Why is there a current and a previous? There's a return, a blank return. Why is it there? Ask yourself these questions, and that will really help you to build your argument and build your intuition and move along this, basically conquer this problem. Cool. Take 5 minutes. Take about 1 more minute or so, and then you can collectively go together. All right, cool. Let's try and walk through this problem together. Let me just move on to the next page. Cool. So again, right, given a sorted linked list of items, we want to remove the duplicates. And then we're given this as an example. We have 1 pointing to 2, pointing to 2, pointing to 2, pointing to 3. And then we want it to just become 1 pointing to 2, pointing to 3. All right, so first things first, right? We see this if statement in the beginning, right? And it's instantly, it should catch your attention because we're returning. So this is almost like if something, automatically just end the method. Like don't do anything else. There's nothing to be done. That should be your logic, right? There's nothing to be done. So when would you ever reach a situation where there's nothing to be done? Like, right, you're given something and there's nothing to be done because maybe that something is invalid. And there we go. I got a in the chat I can see Preeti answered p is equal to null, right? If p is equal to null, you know that there's nothing to be done, and you can just move on. And the reason why there's a checker in this one is because the question doesn't say assume that p will not be null, right? Given the question said assume p will not be null, we could say, okay, we don't have to check that p is null. But given that we don't know anything about the question, it's always safe practice to have an if statement that just checks, can p be null? If it is, return and the method. Cool. Now we have these two int list variables, right? We have these two variables that are pointing to int list objects. And the reason why I can tell they're pointing to int list objects is because they're type int list, right? So really concentrate on these details, right? So you have current and previous, right? Something about the names should tell you what you should assign each value. Let's see if you can get the chat. All right, cool. There we go. Current is equal to p.rest and previous is equal to p, right? Great. And previous is equal to p, right? So it has to do, we're gonna iterate over this. We're gonna iterate over the linked list, right? And so a lot of times in linked lists, you set certain values initially, and then you see over here there's something happening, so you're gonna change and you're gonna modify those values. And so all we have to work with initially is p and p.rest. And the reason why we set current to p.rest and not p to p.rest, or not previous to p.rest, is because, the reason why you set current to p.rest and not current to p, because right now technically you're on p, right? You start off with this, you're given p, so in your head you're on p, so it would make sense to set current to p. But if you set current to p, previous would just be something weird. What would you set previous to? And that's essentially the logic why, sometimes the name matters, because the previous tells us that previous comes before current, and so current must be p.rest because all we have to work with is just p and p.rest. Cool. So current is equal to p.rest, previous is equal to p. We have one while loop, right? Any ideas on what this while loop may be for? And emphasis on one. We have one while loop. All right, I'm seeing some answers in the chat. Current is not equal to null, correct. And the reason why we have this is because we're going to be iterating over current, right? We already checked that we want to be iterating over current. And so because we're iterating, we have this variable current and we're iterating over the list, we want to be able to check that if current ever reaches a point where it's not, where it's null, exit, and that's it, we're done, right? If current ever reaches a point where it's not, null, we want to be finished with this. One reason why this is not, if previous is not equal to null, again, because current comes before, or it depends on how you look at it. It comes before or after previous, right? It's going to be the first thing that's being checked. Because current is p.rest, it's going to be in front of previous. And so if p.rest is going to be null before p becomes to be null, if that makes sense. Convince yourself how that would work out, right? Current in a diagram, current would be in front of p, and so if the list is ending, current would end first and then p would end. Cool. Now you have this if statement, and the way we go about this if statement is, right, one thing to notice: what are you comparing? That is the almost like, you know, the foundation of how you would structure this if statement. In this case, we're comparing an integer, and I can see the chat is really popping, but in this case, I want to make the point that we're comparing an integer. Really think about what you're comparing, right? Current dot first. Current dot first corresponds to an integer. And because we're comparing current dot first, it corresponds to an integer. Clearly, there's something to do with remove duplicates. We want to be comparing something over here. And that's why we do current dot first. What else do we have access to? We have access to previous. There we go. And so now we know that we're comparing current dot first to previous dot first, right? Given that these two are equal, do something. Aha. Now, what do we want to do, right? So actually, let me just use the handy dandy annotator. Let's see. Let me draw something. So let's say current is at 2. So we're at 2 right now, right? And I'm drawing with the cursor, so apologies. But let's say current is at 2, right? Then previous is at the previous 2. And so current dot first, is current dot first equal to previous dot first? Yes, right? Both of them are the value 2. So what should we set previous dot rest? Think about previous dot rest as this arrow. Where should this arrow point to? And where should this arrow point to? And I can see the chat. The chat is saying current dot rest. Exactly, right? You want to skip over this element. So you take this arrow, point to the next element, almost skip over it. And that's essentially what you're doing when you say previous dot rest is equal to, previous dot rest is equal to current dot rest. Make sense? Cool. Okay. Now we have this else clause, right? So given that they're not equal, what do I want to do, right? Given that this is not equal, what should I do? All right, I'm seeing a variety of answers. Any brave soul wanna explain their answer out loud? No one wants to explain their answer out loud?
I'd be happy to try if that's okay.
Go for it. Go for it.
Sweet. So the way my logic's working right now is that current is set to p.rest and previous is p. So if the current element isn't equal to the previous dot first, then the rest of p should stay the same. And because current is already equal to p.rest, I would suggest saying previous dot rest equals current.
Previous dot rest equals current. Okay. So think about, so what is previous dot rest right now? I like your thinking. You're very close. So what is previous dot rest right now? Given that, right? Think about going through this. You know, you start off, you go through this. What is previous dot rest in the first place?
p.rest.
Previous dot rest is, previous dot rest is p dot rest. Exactly, because previous is p, right? But what is p dot rest? P dot rest is current. So then you're saying if nothing happens, set previous dot rest equals to current. But previous dot rest is already equal to current. So why would they provide this line over here, right? If they wanted us to set previous dot rest to current, right? Constantly think about these things, right? There's a reason they have this line. Why is that? What is that reason? And so let me just read the chat. All right, cool. So I have an answer, and I'll go ahead and explain this. Previous is equal to current. Let me just go through this. Previous is equal to current. So let's take a step back to our diagram, little handy dandy diagram over here, right? We have previous set to 2. This 2. Hopefully you can see my mouse or this pencil. We have previous set to 2. We have current set to this 2, right? previous.rest, given that they're equal, we want to set them to it to current.rest, right? But now let's look at this sample. Let's say that actually, let me erase this up a bit. Cool. Let's look at the first example, right? Given that previous is equal to 1, and given that current is equal to 2, are those values equal? Is previous.first equal to current.first? No, it's not. So what do I do in my clause? Well, I want to keep moving forward, right? How do I keep moving forward? I want both my variables. I want current to move forward and I want previous to move forward. But I only want previous to move forward if it's not a duplicate, right? I only want previous to move forward if it's not a duplicate. And let's do another little diagram just to really convince yourself, because suppose they were a duplicate, right? Suppose current was this 2 and previous was this 2, right? And I say previous.rest is equal to this 2, right? Then current becomes this, right? Do I want previous to move forward? No, I still want to compare it with this item, right? Because there could be multiple duplicates in a row. And that's why I don't want previous to move forward if there's a duplicate. But given that there is no duplicate, I do want previous to move forward along with current. And so that's why over here we have previous is equal to current. And finally, the last line, anyone want to explain the last line? Exactly, current is equal to current.rest. We want current to always move forward, right? Irrespective of the duplicates, we want to keep moving forward. And that's why we move current forward only when, not only, we move current forward all the time. And that's why we have this while loop as well. So we're always moving current forward, and we're only moving previous forward if and only if there's a duplicate. Why? Because if there's a duplicate, we move current out of the picture. How do we move current out of the picture? We set previous.rest to current.rest, right? The way current moves out of the picture. Sorry, give me a second. Okay, the way current moves out of the picture. Sorry, say that again. Oh, okay. But yeah, the way current moves out of the picture is that previous.rest is not pointing to current anymore. Previous.rest is pointing to the next item. So I can't set anything to current because current is technically not a part of the list, right? This arrow doesn't exist anymore. Current is just like pointing to another part. So it's not part of this continuation. Okay. If this idea doesn't make sense, we have to move forward based on time. But if this idea doesn't make sense, I really hope you guys come back to this and draw it out on a piece of paper again. That's my best recommendation to you. Okay. Let us move forward.
Do you want me to take over? I think linked list took quite a while. Or
yeah. Okay.
Yeah, I can take over array list if you want.
For sure.
Yeah.
Okay. I'm gonna stop share then.
Sure. We'll do that. Let me share my screen. Okay, so we're going to try to do this very quickly. Okay, so now we're going to talk about array lists, and so just to briefly describe what array lists are, array lists basically contain an underlying array in order to keep track of all the data. So an array list implements a list interface, but the implementation of an array list uses a primitive array to actually store our values. And the good thing about array lists is that it allows us to access any index in constant time the exact same way as we would do with an array, because that's actually the structure that we're using to keep track of our values. And arrays have arrays can be used for ease of access like any generic array, but the benefit of array lists is that we have the flexibility from the list interface, including all the methods that we were talking about before. But one thing that we have to keep in mind when we're implementing arrays is the fact that we have to do this thing called resizing. Because we are using an array as our underlying structure, as we know already, arrays have a fixed size, which means that when the array fills up, we need to resize by making a new larger array and transferring our old elements over into this new array in order to be able to add more elements into our new array, or our array list. But because of our array structure underneath, we need to have this new array. And for our resizing factor, 2 is usually having 2 times is usually a good factor, but keep in mind it doesn't necessarily have to be 2. It could be any factor, but just for the sake of our example here, we're going to be using 2. So just briefly explaining how resizing works. So let's say we have this original 8-element array and it contains some arbitrary 8 values. So when we try to add a 9th element to this array list, what we're going to do is we need to first take the size of our original array or array list, and in this case it's 8, and we multiply it by our factor, which in this case is 2, and we make a new array with that size of size 16, which is here we have an empty array of size 16. So next, what we have to do is we need to copy over all the old elements from our old array, which contains 8 elements, and we just insert them into here. And there are different ways to implement this. You can do array copy, you can iterate through a for loop, but yeah, it doesn't matter. It depends on your implementation. And the last thing we need to do then is we can add our new 9th element the same way as we would do as before, simply indexing into the correct index and just setting the value there. So that's just a really, really quick brief rundown of an array list. And so let's take a look at an example. And because of time constraints, I think we're going to give you guys just a couple of minutes, 2 or 3 minutes, and then we're going to go through the answer. Any questions on array lists in general? Okay, I think we're going to start going over the solution for this question. So here we are going to implement the reverse method so that we're reversing essentially all the elements in our array list destructively. And here, the two methods that we could use here is get and set. And does anyone have any idea of where we would start? So we have this for loop, and what could possibly go into, what would be the elements inside this for loop? Right, okay, I see int I equals 0. Yeah, that's always a good place to start. And notice here, what's interesting is actually that we have this divided by 2 factor. And the reason why we have this factor is because when we're considering reversing the array destructively, which just as a reminder means that we're modifying this array that we're passing in directly, and we're not creating a new array list and implementing the inputting the elements into there. We're directly modifying this array list. And the reason why we have this divide by 2 factor is because think about when we are reversing values, what we're essentially doing is we're trying to swap the values in some way so that in some sort of iteration so that the first ends up at the end and then the end comes to the front. So all we need to do is actually swap these values from the beginning, but we only need to do it half the amount of times of the length of the array, because once we reach the middle, if you think about it, the values that follow it will already be modified the way we want it to be, because they would have already been swapped by the values before. So what we can do here is we can first set I equal to 0 to start our iteration. And then we would use i's less than a list dot size divide by 2. So as we mentioned before, this is because we're taking the size, but we're only iterating through half of the array because the other half will naturally be modified once we complete the swaps in the first half. And then we'll just iterate through with I++. To answer that, don't arrays have dot length? Yes, arrays do, but we are handling array lists, and in our list interface, what we actually use is the dot size method to call the size. And the next line here, we have an int temp. So this variable name doesn't tell us very much, but if we think about what values we could possibly need to store temporarily, what would that be? So we have our iteration value here. What else could we possibly need to store? Yes, I see answers in the chat. alist.getI, that is correct. So the reason why we need to store this value temporarily into a separate variable is because we are destructively modifying this array list, which means that this value is going to be removed. And because we need to input this value somewhere else in the list later, we need to store it somewhere temporary into a different variable first. And any idea of what these two following lines could possibly be? Right. So we have our variable here storing our value, and next we would probably want to actually start modifying and changing our list, right? So since we have the value at index I already, this means that we can set the value of at index I first because we already have this value safely tucked away somewhere else. So what we can do is we set a value at index I to some value, but what value would that be, right? And since we're reversing, that value that we want to put into the first value in the first iteration would actually be the last value. And I see in the chat the right answer as well. So the last value would be array size -1. And because of the way that a for loop is constructed, as we iterate through I, the values that follow in the next iteration would be the last value minus I. So this line would then be array list.set index I because we already saved our value at index I, which means that we are safe to modify this index. And then we will get the value that was originally at its corresponding mirror position, if that makes sense. Are we assuming the list size is even? It's not necessarily an assumption we need to make because the middle value in this case would just be modified to be the same value, so it doesn't really matter. Or yeah, actually, Brian is right. Integer division does round down, so we will not be accessing that middle value altogether. And then, so the next line, anyone, any ideas? It should be pretty straightforward. Yes, so now we modified the front value, the first half of the value. We can now modify the value in the second half of our list. So all we need to do is access the same position where we got our value that we were swapping from, and then we can set it to the temp value that we stored earlier. And so that sets the value at the second half of our list that we were swapping. And finally, what will we need to return here? A list, that is correct. See a question. We can do it the other way around. Yes, in the sense that if you set your temp value to store the value at the end of the list first, so iterating from the back, then you can set the end of the second half of the list value first and then set the beginning. So keep in mind that these two have to correspond in the sense that whatever value you're storing in your temporary integer, you have to modify that one first. Otherwise, there's no point in storing the value if you're just going to modify the other one first, you'll still be losing that value, if that makes sense. How do we know when to use either alist.get versus straight up calling get? So the reason why we need to use alist.get is because alist is actually a parameter that we passed into our function here. So we don't know where this this function actually sits. So it's always safe to take because we're taking the parameter of this function, the only way to be able to get the value is by calling, it's a method of this array list. So we do have to call alist.get. Does that make sense? If we only call get inside this method, we don't know what we're actually going to be calling, because get could very well be another method somewhere else in this code. And it would also not be the correct value because it's not a direct access of the method of this A list that we were provided. Does that make sense? Why are we doing I minus 1 and not just minus I? That's a very good question. That's because remember that all of our list and array indexing are based on 0 index. So the last value is actually at index alist.size -1. And that's just where the last value is because of our 0 indexing. And so minus I is just, Okay, we're going to be moving on since we're already over time. And just a brief summary of when we could possibly use which implementation. So when we would use a linked list is likely when we're going to be accessing, adding, and removing the first and last values, since we have very easy access to the first and last nodes in our doubly and linked list implementation. And another reason when we would use linked list is if we're adding, removing values in arbitrary positions, since it's easier to iterate through a linked list and remove and add nodes arbitrarily in the middle positions than if we were to use an array list. Then we would have to be shifting a lot of values, and the implementation can be kind of complicated in that sense. And a situational example of when we use a linked list is, for example, if we wanted to create an alphabetical list of applicants as they submit applications for a job offer. So the inserting of these nodes could very well be somewhere in the middle and not at the beginning, or not the beginning of the end. And when we would want to use an array list would be, for example, if we were to want to frequently index into values that are not the first and last. And this is a lot faster using an array list implementation because of our underlying array structure. So it'll be direct indexing and much more efficient than a linked list. And another case when we would prefer to use an array list is if we know that we're going to have a really large volume of values, because array list uses an array primitive, which does in fact save a lot of space compared to node, which is a separate object class when the volume starts to add up. So when you have a lot of values, the difference can be quite drastic. And a situational example for when you would use an array list would be if we were to have a large library catalog where each book is tracked with an index number. So we would most likely be indexing into the list quite frequently, and also it'll be a really large collection of values. So that does bring us to the end of the presentation, and we are out of time. So yeah, thank you guys very much for coming, and good luck on your midterm.
Thank you.